Hi, I'm Fernando Pereira, and today we shall talk about an intermediate program representation that suits well the needs of range analysis. This representation gives range analysis the single information property, which you have seen in the last classes, and thus it makes it sparse. The name of the representation that we shall use is Extended Static Single Assignment Form. We will be using a somehow long and convoluted algorithm to solve range analysis. Our algorithm has a number of steps, which you can see in the figure. That's not important now. Each step will exercise some different notions of static analysis that you have already learned in the past, and we will see each one of those steps in details later. For now, what's important is the intermediate representation that our algorithm uses. That's the subject of this class. The first thing that we shall do to solve range analysis is to convert the program to a suitable representation. We want our analysis to be sparse. That means that the range of a variable must be invariant along the entire life range of this variable. So whenever we can learn some new information about the range of a variable, we need to split its life range. Can you stop for a moment and think about what are the program facts that yield new information for a range analysis? We will have to split life ranges at places where those program facts occur. For instance, in this program, we see that k0 is always 0. And we see that the range of k1 is bounded by 100 inside the loop, and it must be larger than 100 outside the loop. We are learning information in the conditional test that you have here in the program. Because we learn information on the conditionals, we shall split life ranges there. This representation that combines SSA with life range splitting at conditionals is called extended SSA form, or ESSA for short. This is a program representation proposed by Václav Bodik and other authors in PLDI in the year 2000. The first part of the algorithm is to convert a program to ESSA form. To do this conversion, to convert the program to ESSA form, we split the life ranges of variables after branches. For instance, in this example, we are splitting variable v0 just after the conditional branch that we have here. v0 here. That allows us to learn with the conditionals. In this example, we create two new variables, v1 and v2. v1 exists in the true part of the branch, and v2 in the false part here. We need a phi function to join the life range of v1 and v2. And we use these intersections here with predefined ranges to constrain the possible ranges of v1 and of v2. Here's the new program, this time with variables split. Notice that we have many more variable names, and notice that we are using the intersections as a way to constrain ranges of variables. Intersections like here and here in the red boxes. For instance, the range of kf is the range of k1 after intersecting it with the interval 100 plus infinite. Notice that some intersections use futures. In this example, we have two futures. Can you think about which program facts lead to the creation of futures? We indicate futures with this notation ft here. So here we're saying that ftj1 is a future for variable it. Futures appear whenever we have comparisons between two variables. In this example, we are comparing variables I1 and J1. Then we'll have futures if these variables are used in the future. Notice that they are used only in the true path of the branch. That's why we don't have futures for I1 and J1 in the false path here. Now, before we move on, can you think about other ways to acquire information for range analysis? There are indeed many other ways to acquire information. For instance, if we know that overflows cannot happen, then we know that after each operation that increases or reduces a variable, the overflow has not happened at that point. In this case, we can split after uses. For instance, if we have an operation such as u gets v plus 10 and an overflow did not happen at that point when the instruction ran, then we know that after u is defined, v must be less than maxint minus 10. Maxint is the maximum integer that we have. So we can split live range after the operation that didn't cause overflows and use an intersection to constrain further the live range of the new variable that's appearing. And with this last observation, we conclude our class about live range splitting for range analysis. In the next class, we shall see how to implement a solver for range analysis. Till there, you feel free to write me with questions or comments. Thank you.